Okay, this is the first video of the new unit that we're starting. Second to last. We're almost there, guys. And this unit is going to be thermochemistry. So basically the chemistry dealing with heat and giving heat and taking away heat and all the fun stuff that relates to that. So this video should be pretty short. It's basically kind of covering what we would have done on Friday if we weren't benchmarking. So the first thing we got to talk about is something that many people in this world confuse and think are the same thing, but we will learn are not the same thing. Okay? So, heat and temperature, they're not the same thing, and we are going to see what makes them different. So, temperature, as we have already said before when we did gases, is that temperature is the measure of the average kinetic energy of all the particles in a sample, right? Temperature, the units are Celsius or Kelvin, and like we said earlier, temperature tells us how fast particles are moving. So if you have a high temperature, that means you have particles that are moving very, very fast. And technically, this is an average of all the kinetic energies, so it's not quite the speed, but it gives you a picture of how fast particles are moving. Higher temperature means the particles are moving faster. So then how's that different from heat? Well, heat is the sum total of all the kinetic energy. So temperature, right, is the average, and heat is like everything, the complete total of all the energy that comes from kinetic energy in a sample. So since it's an energy and a total energy, we measure it in joules, just like because every time we use energy, we're going to be going back to joules. Okay, so energy in life in general flows from high to low, and the same thing is true from heat. If you think about it, and what this means is that heat travels from hot things to cold things only. There's no such thing technically as giving cold energy. When you put something hot in the freezer does not give your, let's say you decide to freeze a hot pocket that you just microwaved. It's not like the freezer gives cold energy to the hot pocket and it cools off. Really, all the heat from the hot pocket flows from your hot pocket to the cold freezer, and your freezer absorbs that heat. But heat always flows from hot to cold, never backwards. And that's kind of, it's a law of thermodynamics. But anyway, so here's some two kind of scenarios about kind of seeing if you can recognize the difference between temperature and heat. Because remember, temperature is just a number that tells you the average energy, but heat is like the total amount of energy from things being hot, which is from particles moving around. So, for example, if a cup of water is at 100 degrees C, or if you have an entire gallon of water at 80 degrees C, which has more heat? And so, even though the cup of water is hotter, the gallon of water at 80 degrees C is going to have more total heat, even though the temperature is lower. Because if you added up all the individual molecules, a gallon of water has a lot more than just a small cup, right? So even if you think like, 100 degrees C is really hot. That's boiling. And I'd rather have a small cup of water at boiling water than a whole gallon of water close to boiling poured on me, right? Because the gallon of water is still going to contain more total heat. Okay? Or here's another one. What about a glowing coal or your body? Like the heat that your body gives off. So even though if you like pull the coal right out, like a charcoal, right out of a grill and it's glowing, and you think of how much heat that has, it's still not going to be as much as your entire body and how much your entire body, the heat that you produce. Because your body is bigger, has more mass, and so the total heat that you put off is going to be greater than a small coal, even though the coal is obviously hotter. So here's just like a couple of things to kind of on the same lines think about it. So if you have 1,000 grams of water at 25 and 1,000 grams of water at 45, which has the greater temperature and why? Well, you're like, duh. Obviously 45 degrees C is hotter because the temperature, the Celsius measurement is higher than 25. Okay, so this has the greater temperature. So let's say you have 1,000 grams of water at 25 and 100 grams of water at 25. Which has the greater heat content and why? Well, because this one has more mass. This is going to have, and it's at the same temperature, right? You have the same average kinetic energy, but this one has more total particles than this does because it has more mass. So this is going to have a greater heat content. Okay, so now we have three things. 1,000 grams of water at 25, 1,000 grams of water at 45, and 100 grams of water at 25. And the question is, which sample has molecules with the greatest average kinetic energy? Okay, so now they're kind of throwing a curveball at you. So you have to figure out what is average kinetic energy. Okay? What do they mean by that? Well, if you either look a couple of slides back or look on your notes, right? Average kinetic energy is equal to temperature. So really what they're asking is which sample has the greatest temperature or average kinetic energy? 25, 45, or 25? Obviously 45, okay? So then the next one, 1,000 grams of water at 45 and 100 grams of water at 45. Which sample has the greatest total energy and why? Again, you got to figure out what is total energy. And remember, total energy is heat. I'm going to practice my cursive. And there we go. Okay. So you're looking for heat and total energy. Well, this one, even though they're both at the same temperature, this one has 10 times more mass than this guy. So this guy is probably the one that will have the highest energy. Okay? So do you see how having mass, more mass, even though you might be at the same temperature, you intuitively know that it's going to have more like heating ability. And that's why we say it has more heat, even though they're at the same temperature. Because temperature is just average what level it's at. And then if you have more of it, then it's going to have more heat power. Okay, so this is relating to something we've talked about before when we did solids and liquids and that specific heat. So this, again, is just like a really quick run through to refresh your memory. Remember, specific heat is the amount of energy required to heat 1 gram of something by 1 degree. So the symbol is C or CP, and it's basically telling you how much energy do you have to put into something before it will raise 1 degree, right? Because some things heat up faster than others, and that's because they have different specific heats. Some stuff heats up really slowly because you have to put in a lot of energy to heat it up. Some stuff will heat up really fast because it doesn't take very much energy to raise the temperature, so it has a low specific heat. Okay? Heat capacity is the total heat that something is holding or capable, right? Capacity is like how much you can hold. And you've actually seen this equation. It depends on the mass of an object, specific heat, and temperature, right? The amount of heat that something has at any moment depends on how much of the stuff you have, its specific heat, and what temperature it's at. And our equation is Q equals MCAT, right? MC times delta T, where Q is the heat absorbed or lost, M is mass, C is specific heat, and delta T is the change. Because remember that delta just means the change. If you're starting at one temperature and going to a new one, that is a change, and that's what delta T is. It's kind of like one thing. You want to treat this all as one thing. Okay? So here's some problems. Well, these are not problems, but this is a table of a bunch of specific heats of common things. Okay, so here's like an example problem. Okay, a 32 gram sample of copper was heated from 16 degrees to 61 degrees Celsius when it absorbed 554 joules of heat. Calculate the specific heat of copper. Okay, so when they talk about heat, you should think Q. Okay, so we have all of our givens. We have 32 grams. We have this temperature change, right? So that sounds like a delta T. And then we have 554 joules of heat. And heat is going to be, oh, don't do that. Heat is, don't do that, Q. Okay? So when you set up our givens, the mass is 32 grams. My delta T, 61 minus 16 means I changed 45 degrees. My Q is 554 joules, and they want me to calculate specific heat, which is C. Okay, there's my equation. So I have, my Geoffroy method. I have my givens. Here's my formula. Let me plug in these numbers for my work. And so you see that I have all my numbers except for C. So algebraically, I'm going to solve for C by dividing by these two guys. Okay, so these two multiplied is 1,440. Divide both sides by this to get rid of it, because I want to get rid of him. So that's going to give you C equals 0.3866 joules per gram degrees Celsius. Okay? So, simple enough. Example 2. The specific heat of aluminum is 0.899 joules per gram degrees Celsius. If a 75-gram sample of aluminum is heated from 25 to 40, how much heat did the sample of aluminum gain? Okay, so again, looking for my givens. Okay, they tell me specific heat, and they already told me that. Well, that's going to be a C, right? Here's a grams. Grams gives me mass, that's M. 25 to 40, that sounds like a delta T because I'm changing temperature, right? And then they want me to figure out how much heat, and heat is Q, right? So again, set up my givens. C is 0.899, M 75, delta T. I went from 40 to 25, so that's 15 degree jump. So I changed 15 degrees, and I want to know Q. So that's G. F is formula. Q equals MCAT. Plug in your numbers. I have nothing to solve, right? Q is over here by itself, so my algebra is done for me, and that means Q is 1,011.38 joules. Again, problem's pretty straightforward, okay? But here's a challenge question. Let's say if 800 joules of heat is added to 20 grams of water, and the specific heat of water is 4.184. Okay, so if you add 800 joules of heat to 20 grams of water at 30 degrees C, what would the final temperature of the water be? I'm actually not going to work this question in this video, but if you sit down and think about it and then bring me the answer later on, then you might get a surprise or some sort of prize for getting the challenge question right. So see if you can get the challenge question and then come tell me later what you think it is. Okay? So that is the end of this video, and we will continue talking more about heat and how much heat stuff gives off on Monday and Tuesday. Have a good weekend.